Imagine you are riding a bicycle across a rolling landscape. When you pedal uphill, your slope is positive. When you crest the top, you are briefly perfectly flat with a slope of 0. And when you coast downward, your slope is negative. If a perfectly steady, positive incline is mapped onto a graph, you get a straight line, like the equation y equals 2x. This line has a rigid, unchanging rule. For every 1 step forward, it rises exactly 2 steps up. Its steepness is identical everywhere you measure it. Straight lines are easy to measure because they never deviate, but calculus was invented to decode curves, where the rules shift continuously and the steepness changes at every single millimeter along the path. This graph plots the curve y equals x squared. If we isolate a single point, say at x equals 2, we face a new problem. How do we calculate steepness when we are only looking at one exact coordinate? We can visualize this instantaneous direction by balancing a tiny, perfectly straight ruler against the curve at that specific location. That straight line is called the tangent. The math creates friction here. Standard algebra requires 2 separate points to calculate any slope. Finding the steepness of one isolated point seems contradictory. We solve this using a limit. We plot a second point slightly further up the curve, and then slide it downward. As the distance between the 2 points shrinks toward 0, the connecting line rotates until it locks into our true tangent. Calculus provides a mathematical shortcut to skip this sliding process entirely, known as the first derivative. For x squared, the derivative is 2x. By plugging in our coordinate of 2, we find an exact instantaneous slope of 4. The first derivative acts as a precise gauge, reading the exact steepness of a curve at any given moment. Let's track this same curve all the way down to its absolute bottom. Think of a ball rolling into a valley. Right at the base, before it can begin traveling upward again, it must rest perfectly flat for a fraction of a second. To locate this flat resting point mathematically, we simply take our first derivative, 2x, and set it equal to 0. Finding where the slope equals 0 introduces a new question. How do we prove mathematically whether that flat spot is the bottom of a valley or the top of a hill? We differentiate our equation a second time. This second derivative measures the rate of change of the steepness itself. Our second derivative equals positive 2. Because it is positive, the overall slope is continuously increasing from left to right, bending the curve into a concave up shape. It forms a visual smile, confirming our flat spot is a minimum. Let's test this logic. Here is an inverted curve, y equals negative x squared. Pause for a second and try to find its first and second derivatives. The first derivative is negative 2x. Differentiating again gives a second derivative of negative 2. This negative second derivative dictates that the slope is constantly decreasing. The shape bends concave downward, mimicking a frown, proving that this particular flat spot is a maximum peak. The first derivative locates the flat turning points, while the second derivative measures the bend of the terrain, telling you exactly which type of terrain you are standing on. We can apply these pure math rules to physical problems. Suppose we want to cut corners from a flat piece of cardboard and fold it to create a box with the absolute largest possible volume. This graph charts the resulting volume. The relationship between the cutout size and the total space forms a much messier polynomial curve, 600x minus 100x squared plus 4x cubed. The algebra is heavier, but the structural logic is identical to our simple parabola. Finding the maximum volume is as simple as finding the highest point on this new graph. To lock in on that peak, we calculate the derivative of the volume equation and solve for exactly where the slope hits 0. Here is your core logic matrix. The first derivative, y prime, answers a single question: how steep is the curve at this moment? The second derivative, y double prime, answers the follow-up: how is that steepness changing? If the second derivative is positive, the curve smiles upward into a minimum. If it is negative, it frowns downward into a maximum. The first derivative is the map you use to locate a turning point. The second derivative is the compass you check to verify if you have found a valley or reached the peak.